Hi everyone, my name is Emily Reed, and I will be presenting our work on sampling-based, nonlinear, stochastic optimal control for neuromechanical systems. This is joint work with my co-authors Marcus Pereira, Francisco Valero-Cuevas, and Evangelos Theodorou. Controlling neuromechanical systems is important for advancing rehabilitation and treatment technologies, advancing theories for the restoration of motor movement in patients with disabilities, and creating robotic exoskeletons and prostheses for amputees. State-of-the-art prosthetic devices currently do not match the versatility of human movement in neither functionality or ease of use. Commercially available prosthetic devices use simplified control techniques like on-off control or proportional control to translate EMG signals into motor commands. However, only a small number of tasks are achievable with these methods. Human-in-the-loop BMI systems relying on pattern recognition to match specific EMG signals to motor commands have been developed in clinical settings, but these computationally demanding methods rely on noisy physiological signals, require a long learning time, and must be tuned across different users and even different settings for the same user, like posture, electrode position, and fatigue, which ultimately leads to a variable performance. However, we believe that prosthetic devices will become more lifelike when they become capable of mimicking their biological counterpart, including both in control and in design. In the design sense, tendon-driven systems have multiple advantages, including backdrivability and motor placement close to the body, but are known to be difficult to control. We address this control problem head-on as it can open a new field of opportunities in wearable devices, prosthetics, and functional augmentation exoskeletons. SOC, stochastic optimal control, is a natural candidate for controlling neuromechanical systems because it provides a theoretically rigorous framework for precisely controlling highly nonlinear, noisy systems. SOC seeks to find the control input U at each time step that is optimal with respect to a prescribed cost function J, subject to the stochastic dynamics of the system. In general, the cost function describes the goal of the problem. The minimum cost function is called the value function, B. This problem is difficult to solve because the optimal control solution relies on finding the gradient of the value function. In the context of our specific problem, the goal is for the index finger to reach the final prescribed tapping position specified by joint angles while minimizing the amount of force applied to the tendons necessary to achieve this final goal. We compare and contrast three SOC methods for controlling a tendon-driven, planar, three-joint human index finger modeled in simulation to perform a tapping task. We present the index finger model as a system of stochastic differential equations. Here, theta specifies the joint angles and joint angular velocities. I is the inertia matrix, C is a vector of centripetal and Coriolis forces, B is the joint friction matrix, T is the torque vector, M is the moment arm matrix, and F is the tensions on the tendons. The third equation is used to model delays in the generation of tensions on the tendons. Tau is the time constant of muscle activation, which is 40 milliseconds in all simulations. U is the control vector, and W is Brownian motion noise vector with covariance sigma squared times identity. For our simulations, we have excluded the abduction-adduction movement of the MCP joint, so we only examine planar movements. Therefore, the state space formulation of the index finger model has a dimensionality of 13, corresponding to 6 states for the joint space kinematics and 7 states for the tension applied on the 7 active tendons. Since tendons can only pull, imposing the last constraint, U greater than 0, ensures that F is greater than 0. The figure shows a model on the human index finger and its joint angles. Now I will briefly describe each of the 3 SOC algorithms that we tested. Each of these algorithms can be used with nonlinear stochastic dynamics. I will start by outlining Iterative, Linear, Quadratic, Gaussian, or iLQG, which aims to solve the problem with an LQG-like approach for a nonlinear system. In a regular LQG problem, the dynamics are linear and the cost function is quadratic. Therefore, iLQG starts by discretizing and linearizing the dynamics using Taylor's approximation around a nominal trajectory up to the first order. The main idea is to take expansions on both sides of the value function up to the second order and equate the terms. By substituting in the expanded terms and taking the gradient with respect to the control, we obtain a control update law, which can be added to the control policy at the current iteration. Convergence is determined when the process of taking subsequent Taylor approximations and performing LQG updates does not lead to an improvement in the objective beyond a given tolerance. The main advantage of iLQG is that it is computationally simple. MPPI is an extension of the model predictive control formulation, where first a nominal trajectory is guessed. Next, multiple samples of controls are taken from a given distribution. Using these controls, their state trajectories are predicted around the nominal trajectory. Then the cost for each trajectory is calculated, and the trajectories with a lower cost will receive a higher weight. Therefore, the control update law is, in a sense, a weighted average of the sample controls that gave the best trajectories in terms of the minimum cost. This best trajectory then becomes the new nominal trajectory, and the process is repeated until a finite time horizon is reached and a final trajectory is obtained. The main advantage of MPPI is that it avoids the differentiability requirement for the dynamics. The stochastic optimal control problem is mathematically connected to a system of forward-backward stochastic differential equations. We solve FBSDEs using a deep recurrent neural network that approximates the gradient of the value function at every time step, which leads to the optimal control. The main advantage of FBSDEs is that it relies on fewer assumptions, is more general, and better approximates the value function. I now present the main results of the paper, which describe the performance of each algorithm in controlling the human index finger in simulation to reach the target joint angles, shown in the figure as a black dotted line. We observe that iLQG in red produces the highest variance and is less likely to reach the desired target than the other two algorithms. Note that the shaded red region shows the standard deviation and the thick red line shows the mean trajectory over 128 runs. FBSDE in green provides very good results with the lowest variance and can consistently reach the desired target. MPPI gives perhaps the best results because it has the best rise times to the target joint angles and smoother average trajectories. While MPPI is able to converge the fastest, when we zoom in, we notice that it doesn't always reach the target at the end time. We summarize our results in the following table. While iLQG may be the simplest computationally, it requires that the dynamics be differentiable and gives only adequate performance in controlling the human index finger. FBSDE gives consistently good results, however, it is the most computationally intensive method. It gives good performance results. MPPI avoids the differentiability requirements of the dynamics and gives perhaps the best performance results with the best rise times. However, because it is computationally intensive, MPPI requires a GPU to run in real time. Our results showed two SOC methods, namely MPPI and FBSDE, capable of accurately and consistently controlling a nonlinear tendon-driven finger to reach the designated target without a prescribed trajectory in the presence of noise. We conclude that MPPI gives the best results overall because it finds the optimal control law by taking a weighted average of several good controls. In the future, we plan to test these methods on tendon-driven hands and actual manipulation tasks, including intermittent finger object contact. We would like to gratefully acknowledge our funding sources and thank you for your attention. Merci beaucoup.